if I have an object, right? And the object is moving with constant velocity, right? What you will remember is that as the object moves around the circle, direction is always changing, right? But although the speed is constant, and the direction is always changing, that means that the velocity as well as the velocity changing as well. And we know that if the velocity is changing, then the object is right. So the object has an acceleration. Right? Of course, we'll name it properly in a little while, right? And if the object has an acceleration, then it has what? This implies it has a from Newton's second law, right? This implies it has a resultant. It has a resultant force acting on it called what? We call it the centripetal force. Right? And please remember that if your velocity acting, if it was just in this direction, perpendicular to this direction, right? Perpendicular to this direction is the direction of the acceleration and your centripetal force. All right? So this here is the Form 5 stuff that I need to remember, right? And now we will start. Yeah. Huh? I got you in mind that. Huh? All right. Okay, so just make a note of that. If you didn't hear it before, write it down because two important things comes out of this, right? Number one, this body has an acceleration, and most important is that it has a resultant force acting on it. Okay? And we're going to speak about that resultant force now. All right, so let's draw a little circle, right? And that circle, we have the object initially here. And yeah, this is for the end. I don't think some of them not there, so I'll do it. And I should Darwin of paying attention. Okay. So if you have a circle, right? Let's say the pendulum and the pendulum moving in this vertical circle here. Right? Here to here, let's call that the radius. Right? Here to here, we call that something called your angular displacement. Right? R is your radius. Theta is what we call your angular displacement. Again, all this in the notes except the diagram, right? The diagram in the notes. The velocity at any particular point is perpendicular. Right? That velocity, we call that the linear velocity. And then we're going to go through a few things, right? Right, get that diagram. I'm going to add something to that. I think you know already. Freedom, everyone ready? That's right. Ready? Are you ready? Right, so we're not focus on that diagram, we're going to develop a few relationships, right? Okay. Open the gap. What? Huh? The last thing was one after the last. Yeah. So, well, 3 minutes. I want to show you that. So I want to find out people live now. Yeah, that's it, live. I'm not ready. 2 minutes again, I'm going to start the develop this, right? But it's a big All right, ready? All right, are you ready? Right, number one. So, we should know what a period is, right? Period is what? Period is T and it's the time for one whole cycle, right? So the time it takes for one cycle of T, and we also know that period is also equal to 1 of them. That's okay? Nice. So there's a new quantity that we need to learn, and that quantity is what we call angular in its circular motion, we call it angular velocity. Those who do simple harmonic motion, we call it angular frequency, right? So what is angular velocity? Angular velocity is, you all recognize that at each point I am giving you the straight line velocity, right? Angular velocity is the velocity it's traveling with as it moves in the circle. Okay? How do we find angular velocity? Same formula. Same formula. Angular displacement divided by time. Same formulas as velocity. Velocity is displacement in time, right? So angular velocity is your angular displacement divided by time. All okay with that? Nice. How long will it, or what would theta be if we complete one whole cycle? If we complete one whole cycle, theta is what? 360 or reason radians in. Or 2 pi, right? So after a complete cycle, theta will be 2 pi because we're working in radians, right? And how long that will take? capital T. Correct? So it will take capital T to travel 2 pi. Right? So what does that say? That says that omega is equal to 2 pi on T. Right? But remember, and we know that F is equal to 1 on T from this formula here. So this means that angular velocity is equal to 2 pi by x. Okay? And the SI unit, I didn't give it here, but the SI unit is radians per second. Not meters, right? Radians per second. I think, this year, right? That was the thing that we looked at the beginning, just to explain circular. Nice. So now we know about this new quantity called angular velocity. Angular velocity is 2 pi f. I gave you the SI unit. Now we could go back to linear velocity. And we know that linear velocity, which is v, is displacement divided by time. Right? Anybody remember the display? How to find the displacement? How to find this? I find here to here, that distance. Right. So you remember arc length? Arc length. Arc length is r theta divided by t. That's okay? So that will be r by theta on t. What is theta on t again? Right. So what does that mean? It means that linear velocity is r by angular velocity. That's okay? Right? So you have two new ones to add in. Okay? So we know about linear velocity now during circular motion. We know about angular velocity and we know about period and time. So now, as we said in our small definition, if we have velocity, we have acceleration, and we should have a resultant force. So let's go to acceleration now. Right? So as we said, since velocity is changing, this implies acceleration. This implies acceleration. So how do we find acceleration? Let's be more specific here. This is centripetal acceleration. Right? We don't have to prove this one anymore. Right? So we can just learn it. Acceleration is v squared by on r. Sorry, is omega squared r, or v squared on r, or omega v. So these are the three formulas that we could use to find centripetal acceleration. Okay, we don't have to prove this anymore, right? There was a nice long proof that used to do for this one. Okay, so again, because the velocity is always changing, then the body has an acceleration, and that acceleration is given by this. That's okay? So that's following that. And because the object has an acceleration, it should have a force, right? A resultant force, right? And that resultant force right? So hence a resultant force exists, right? And it's called your centripetal force. The symbol I will use is here. If I know A, how to find CF? If I know E, how to find CF? Centripetal force. F is equal to what? ME. So if I know E, this will be M by E. Correct? Yeah? Just M in front of all. MB squared on R, this is one of the most popular ones, right? This one here is hardly ever used, right? But the most popular is this one. Okay? So formula wise, these are all the things that we need to know to send centripetal force. Okay? And you understand where all the things come from, right? Right? You understand why it is we be able to talk about acceleration because the velocity changes, and be able to talk about the centripetal force because there's an acceleration. Okay? But I want to spend a little more time on this particular course here. All right? Start going back to that diagram. Online, are they okay? Yeah. So I want you to bear in mind that centripetal force is a resultant force. It's not a force acting on the object. It's a resultant of the forces acting on the object. All right. So we're going to take a look at an example here. And you just simplify the example too, right? Of what centripetal force we have here, right? Ready? I'll wait once. So that's so say a diagram, right? Draw the string and draw the object at that particular point there. That's the lowest point on the circle, right? At the lowest point on your circle, I want you to draw your century, draw the object. Right, at the lowest point there, sorry. Let's just draw the string and then draw the object. Draw the string and the object. String pass ball again. String pass ball again. Yeah, that's it. I'll fix it and see it. Yeah. Never see. Yeah, we went through it. All right, ready? So here's what you're doing from right? What I want you to do, and or somebody could tell me, right? Pete, still looking so interested in this. Pete, can you tell me the forces acting on this object? You don't know any of the forces acting? Yeah? It's a vertical circle. Yeah. It's a vertical circle with the string acting vertically, and yeah, it have a string holding the pendulum, holding the ball. Tension acting way. Right? So you have tension acting upwards here. Right? T is tension. Gravity is not force. Weight, nice. So you have weight acting here. Well, it's not moving, it's stationary. So does any other forces acting on it? No. So yeah, it's a resultant of that's what I'm bringing to now. So acting on the object, the forces acting on this object is weight potential, right? But remember, it's moving in a circle, right? And the resultant of these two forces, the resultant of those two forces is what will give your centripetal force. Correct? So what direction What direction will the centripetal force act in? I think I drew it here earlier. Centripetal force always acts to one center, right? So the centripetal force is what? Same direction of tension, right? Opposite to weight, right? Are you okay with that? So therefore, centripetal force is the resultant of tension minus weight. Okay? Always remember that, right? The resultant of the weight and tension gives centripetal force. Right? Well, not weight all the time, but right, the resultant of the forces. Right, write that first, then I'll give you just one little thing to write. The resultant okay. So the centripetal force, if I had to do a free body diagram, not writing centripetal force. All you're doing is you're writing tension and weight, right? Centripetal force the resultant of those two. Okay, nice. Okay, now just one small note underneath this. Note that the centripetal force. Note that the centripetal force. Any questions online? The centripetal force is the resultant of the forces acting towards the center is the resultant of the forces acting towards the center of the circular path. Next subheading, just write vertical circle. Head up vertical circle. Right? Let's do more paper now. See if we can find centripetal force at A, B, and C. And at A for you already. Right? See if we can find centripetal force at A, B, and C. Right? I did A for you already, right? Find centripetal force at B and C now. Good time. And when you're finished, you can find tension on it. Oh yeah, try to be answering. Right, put your forces in, right? And then go out 95 go. Now you're gonna get to there. Now you're gonna get through. Something so true. All right. Right, so let's start here. Here, tension always acts towards the equilibrium point. Weight will always act vertically downward. Right? Well, what are the forces acting towards the center? Tension alone. Okay? So centripetal force is tension. Right? Here, we have weight acting downwards and tension. Centripetal force acting towards the center, these two in the same direction. So that will be W plus T. Okay. I also have to find tension, right? So tension here is what? Tension at P is what? Just rearrange. Centripetal force minus tension at C is what? Centripetal force alone. And tension at E. Centripetal force plus weight. So by looking at these formulas here, which one, where is tension maximum? At A, B, or C? A, B, or C? Tension is maximum where? What's your formula? What's this one? What's this one? A, right? So tension is maximum here. Does it make sense that tension is maximum here? Where do you expect this string to break if you were total this in a circle? Most likely the string will break here, here, or in between. Most likely here, right? If the string break, it will break at that point and it will travel. If the circle is going in this path, it will travel like that. That's good, right? So if it's moving like this, and the string break, most likely the string will break here because tension is maximum and it will travel a path like that. What it's looking like? What type of motion? Parabolic motion, right? So I can take a circular motion question and turn it into a projectile motion question. Right? Nice. Why does it didn't include weight here, Jacob? Why I didn't include weight here? Right? You're close, but I want better answer than that. I'll give you a small note on that. Why it says I did not include weight here, only include tension. But I included here and here. Close it. Close it. Right. Centripetal force is a resultant of the forces acting towards the center, and this is not acting towards the center, but I really like Mackey's answer. He said the resultant of these two is here. That is not the circular path, right? That's not towards the center. You're seeing that? The resultant of these two is here, which is not acting towards the center. You okay with that? All right. So this is a vertical circle. So if I take an object and I move an object like this object is moving in a vertical circle. It was, I had a nice one where you were able to find the velocity. Huh? Yeah, no, it boosts by some right? But here's what we're going to do now. I'm going to take the same pendulum with a string attached to a fixed point, and I'm going to move it in a horizontal circle. Right? Push up on my just see that. Right? So I have a point, I have a string, and a pendulum, and I'm going to let it move in a horizontal circle as opposed to a vertical circle. Okay? So we're going to move it now in a horizontal circle. Right? But the same principles will apply, right? And then we could try some questions. Let's take a look at the horizontal circle. Again, this in your notes, except you have a diagram, right? So you will see a little space, you have to draw in that. In case anybody print. All right. So I want to take a look at the horizontal circles. Are you okay online there, Darian? Pay attention. Oh yeah, the game, Darian. Darian, yeah, but if you have any phone, you can message me and say something. Darian, not even paying attention. Listen. All right. All right. So let's say you have a pendulum here. Pendulum with its string is at an angle theta to the horizontal, and it is moving in a horizontal circle, right? Of course, if it moves in a horizontal circle and you draw it, it will not look like a circle here. It'll look like a oval, right? But it is moving in a horizontal circle, right? Right. Again, I want you to draw this one, put all the forces acting, and see if you could tell me what is centripetal force is. Right? So draw it, you have the string, bob, moving in a horizontal circle. Put in the forces missing, and find the centripetal force. Put in the forces missing and see if we can find the centripetal force. I give it yeah. Right? Huh? Then we'll start some small questions, right? I mean, so that's the object, right? So should I weight acting what? And tension acting when? Right? So you want to figure out now, was the force acting towards center? Because only the forces towards the center will contribute to the centripetal force. Right? So think about it. I give you an angle for a reason. Huh? I could be not, maybe not be. Yeah, here, could see, not here, not here. But see here, here, technology. Iran, already, Iran. Still on again, sure. Yeah. All right, so we have here, right, Jacob? Where do we? The weight acting vertically downward, tension is where? Going up here towards the equilibrium, right? Right. But the horizontal circle is here. So what's the force acting toward the center here, Jacob? What you have to do? Is it the weight? No, because the weight acting vertically downwards. So it has to be something to do with the tension. So what do you do with tension? What is called the word? You have to? Yeah. Thing. R. You have to resolve tension. So you have to resolve tension horizontally and resolve tension vertically. Okay? So horizontally is what? Opposite theta. So that will be T sine theta, and adjacent will be T cos theta. That's okay? So Shanita, pronounce it right? No, pronounce it. Shazana. What contributes to the centripetal force? Which one? Which force acting towards center? These side. Right? And because it maintains a horizontal motion, it's not moving vertically yet, but vertically, just staying horizontally. Then these two have to be what? Those two forces have to be equal. Well, yeah, cancel. Right? Marquis, some more things is answer when finished, right? All right. So that's a horizontal circle. There's a next version as well. There's a next version where what did I use last time? I use this. Right? There's a next version where right? I'll go here. Right? That's the pendulum, right? So one version is like this. Right? 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 One version is like that, where you have a horizontal circle. Well, we will see the next one. And the next version of the horizontal circle is this, right? This one? Right? The next version of the horizontal circle is like this. Right? The next version, somebody had a nice little thing last time. But a next version of the horizontal circle is that. Right? So you have your string, right? You have your string and the club, right? And the horizontal circle like that. That's okay? So if I draw that, Jacob, you're shaking your head there. If I draw that version instead, right? You have the string, bob, moving in a horizontal circle. Right? What centripetal force here in this version of it? What? Right? This is the horizontal circle as well. Right? Huh? Don't have to sit there, and then I can extend this one. I can't extend this one. Right. We have a horizontal circle, right? As I showed you here. As I showed you here. What is providing the centripetal force as I move this now? As I move this in a horizontal circle. Right? What is providing the centripetal force here? Right? Tell me the forces acting here. Obviously, it have weight and tension acting where? Right. So, Jacob, what is providing the centripetal force in this version of the horizontal circle? What is providing the centripetal force? Think of the forces acting towards the center. See? And then you do with the weight? Just touch. That's okay? Yeah? I believe you're all right. Just a quick by just looking at them, right? Which one will provide a greater centripetal force? Which one might have a greater centripetal force? Horizontal circle like this or like this? Look at the values. This one, right? This value bigger than t sine theta. Okay. Right, so you're looking at treat as circles, right? Of course, all of this also observe like if it's an object moving in a roller coaster, if an object moving around a curve, like a car driving on a curve, right? All these centripetal forces also observe, right? But we'll do that next. Right? So let's see if we can put all this together now in a calculation. Online, any questions? Alright, let's try this one here now. What type of circle is that? Horizontal circle, right? The first type that we did, right? Alright. Come on, paper now. Draw it up now. Draw it, and we're gonna try to find these things together.
Yeah, firstly, I got also I got your friends.
Yeah, do that. Right, after you draw the circle, of course. Right, after you draw the circle, put in the mass is 50 grams. Radius 0.2. It gives you an angle 38.3 and time for one revolution. Alright, so adding your weight. Right, your weight will be what? Oh, that's not okay. Like a mass. Come, we can about that one. Right, so you should get 0.5 newton, right? Yes, what they calculate will be doing. What they calculate will be. You don't need this much. Right, remember you have tension here, adding everything up. If you don't want this theta, I don't really want this, but I want theta here. Right, find theta. Find theta there. Right, how do we find omega again? Omega is what? Based on the formula that we learned. Huh? Theta 1 for what? Well, not that theta, another theta. Which one? right? We could use 2 pi on period, right? We could use 2 pi on period. Remember, if you use this theta, you have to get the time to travel, right? Without between that angle, we don't know that. Time for that angle. No, I one revolution. So what they gave you there? 0.8 is the what? Marquis, 0.8 is what? Period. Period. That's very good. That was 6 questions that we answered. Huh? So that'll be 2 pi over 0.8. And then if you answer in radian, put the time on. Lana, give it up. Sure. Good. So that's the next part. So omega is what? What is 2 pi over 0.8? Right? 2.55 radians per second. So one of that. So you find in the accent better acceleration. Right. Go ahead. Work it out. Let's see if you'll figure out the last part. What the formula you centripetal acceleration rate? What's the formula you're going to use for centripetal acceleration? Sorry? Per second, radian, per second. S to the minus 1. Yeah, wait. How we get the centripetal acceleration? E is equal to what? Repeat this. Huh? Check the formulas. What? I give you a long list of formulas there. A is equal to what? W. You have P. Where? W squared R. Yes. It's called omega squared, not W. Omega squared R. Right? So that's 2.55 squared by what R again? What's the radius? 0.
So you can play it, it's base and 0.5. Yeah. You could just skip this guy. And like the legal part, what's up? And you can play it by 0.5 saying
And E. Oh, and you give me part 2. Yeah, we come to part 2. Just what part E? Yeah. And that's what you give me? 0.5. Oh. I thought that's what you give me. What is that? Right, 1.25 meters per second. Okay. Square. Sorry. Part 2. Part two. Javed. Javed. Javed, how are we gonna get centripetal force? Check your formulas. Centripetal force is what? Yeah, we do not see the carry diet. Just multiply by mass. And you already have acceleration, right? So you multiply the mass by omega squared r that we already have. What's the mass again? 0. No, 0.05. Right? Multiply by 1.25. That's okay? So we just simply multiply the mass by the acceleration, I say. No? Okay, that's real basic. You follow? For sure? Let's say yes now. I carry the eyebrows all the time. Where's that it? 0.0625, right? You got it, right? Right, now for the hard part. Even if I 2 minutes. Online, you can figure out that part, you can message the answer. What's the tension in the string? Look back at what we just did. Find the tension in the string. Find T. You have 2 options. Anyone you like, you can use it. Please pay attention to where theta is, right? Find tension in the string. Right? Right, so please remember that if here's theta, and that's tension, and here's weight, we said that centripetal force was equal to T sine theta. Okay? Said centripetal force is T sine theta. So T will be centripetal force over sine theta. Right? For centripetal force again, 0.625 over sine, right? Again, the diagram I gave you had theta next to the normal, right? They gave you theta next to the surface. So you have to remember that theta will be 90 minus 38.3. Okay? So that's how much? 51.7. How much is that? Can I look it out? 0.08. Could I have done this on next week? Could I have done this on next week? Use 38.3.
And I guess you're friendly.
What you said, but of course equals to. The cost theta. Or sine as well. Okay. But if you had used the cos theta. Because on top here is 38.3 and down here is also 38.3. Yeah, so if you had done that, you would have. Right, question, we can also do the next week. Instead of using centripetal forces T sine theta, we could have also said that W is equal to T cos theta. And work it out. Okay, either could have. No, you're very same answer. All right, any questions online? Want to go again? Want to do our next one? We do one more, that'll be good. Katrina, are you okay there? Darren, if you're listening, you okay? Sorry, you got you? Sorry. Yes. All right, let's see, let's try one more, right? Let's go again, Oliver, next one here. All right, last one, Marcus. Marcus. First side. Second time, second. It's still never.
And it took out the SEO because all of the shit, like direction.
It's an extra time with the shape panel. Shape.
Yeah. So that's the time I think.
Huh?
That was the time.
It's a good shape panel. Oh, yeah. Try that, please. Oh, panel, this up. Oh, yeah, try that, please. Oh, okay. Yeah, I know, yeah. You just pass 5 minutes, pass out for your Activity and the first please. Everybody else, thank you, read it. Watch out, watch out. Everybody else trying to read it. Any question? Hurry up. Huh? That's awesome. Please. Everyone take long part 1 and 2 is in the part 3. The 10 I use 10. Right, you'll GL 10. Last question, we're done. Right, part 1 and 2, as I said, should be easy. It's part 3 you have to figure out, right? Right, they gave you the mass of the stone, they gave you the length of the string, so you know what R is. And they give you what tension is, max tension, right? See what I'm going to help you find a way. Where will the string break again? Highest point or the lowest point? Lowest. All right, go ahead. Now, I hope it's not.
No, but the time something that's been. So it should.
Right, I'm correct now, right? All right, so you should have part one and part two already, right? Right, you have your circle. At your highest point, draw the forces acting. Right? So that's at the highest point, and at the lowest point, you have sorry. At the lowest point, you have tension and you have weight. Okay? In what position along the vertical circular path is it most likely to break? Right? Now the bottom, we tell them at the lowest point, right? Right? Because it has very good, because it has max tension. Very good. And at what angular speed will the spring break? Right? So what we have to focus on is where the spring will break, right? And we said the spring will break at the lowest point, and what do we know happens at the lowest point? Tension is equal to Cm plus weight. Do we know tension? Tension is 20. Do we know Cf? No. Cf is what? M omega squared R, right? And we can find the weights. Correct? Yeah, we can find the weight, right? So we know what the mass is. Plug it in now. So 20 is equal to the mass. The mass is 0.5. We go to omega squared. R is how much? R is 0.5. Convert how to be in meters, right? And the weight will be 0.5 by gravity. As I said, you can use it as 10. That's okay. So all we really have to do is pull what we know happens at the lowest point. All right. Book it out and tell me what you get for omega. Anybody get something online as yet? Solve for omega, please. Alright, any answers? What I got for bigger? 7.7. Huh? From here, the square root, huh? So I have 20 minus 5, which is 15. 15 divided by a quarter, 15 multiplied by 4, which is 60. So I have the square root of 60 as the answer. Square root of 60 as the answer, it is 7 point something here. Is that right? What you all got? What you all got? Square root of 60, right? Alright, nice. So we'll stop there for today.